All right, guys, so I'm going to do 10.3, number 9 and 10. If you want to watch this, go ahead and watch this. If not, just keep quiet and stay focused on your assignment there. But this is number 9 and 10, 10.3. Okay, so it says let j of x be x squared, k of x is x cubed. Does k of j of x, that's when I put the j of x, this one, inside of this, equal j of k of x, that's when I put this one inside of this one. Does it equal each other? Okay, so on the one hand, k of j of x, so j of x, x squared, goes inside of x cubed. Okay, that's the first one. Second one would be x cubed goes inside of x squared. So are these the same for all possible values of x? Well, this simplifies to x to the 6 when you multiply. This simplifies to x to the 6 when you multiply. So looks like they're the same. This can be fine for an explanation. You can also say that a power raised to a power you multiply exponents. So 2 times 3 is the same as 3 times 2. Okay, that's for number 9. So yes, the same. Does that look good? Yeah. Does that make sense? Yeah? Okay. Number 10, so does s of t of x equal t of s of x? So let's try it again. And if we put t of x, that's this one, x minus 3. If we put that inside s, so watch this, and I'll use different color for this one, but this x value is now this x plus 3, so it looks like this. You see? T of x is inside the s of x function, so I put in x minus 3 in for x here. So this is s of t of x. And the other one is when we go s of x is inside t of x. So I put in, I'll do this in black then, I put in x squared plus 1. That's s of x. That's got to go inside t of x. And of course it goes in where the x is. So it's going to be like this. I guess maybe I'll do red here again. So this is t of s of x. Now I believe that looks right. Anybody double check that? Any see any problems with that? Okay, if that's correct, then we have to ask ourselves if this is equal. We probably should expand just to make sure. So this is going to be x squared minus 6x, and this is going to be plus 9 plus 1. This one's going to be x squared minus 2. So right away you can tell that they're not going to be the same, looks like, right? Yeah. So they are not the same. Explain, I mean, if you just show your work like that, these two are not equal, so not equal. And this work is enough for me for explanation, okay? Okay, that's your question? Yeah. Okay. Any other questions you have about chapter 9 or 10? Moving up to test tomorrow.
Can you do 13D?
Yeah. 10.3, 13D? Yeah. Okay. We got some nervous laughter for 13D, so let's see what D says. Okay, so Jordan is examining her car expenses. Her car uses gasoline at a rate of 6 liters per 100 kilometers, and the average cost of liter of gasoline where she lives is 123 per liter. Okay. So write the composite function that expresses the distance driven in terms of the cost of gasoline. So distance driven is going to be your kind of like outside function in terms of the cost of gasoline, so your cost is going to be inside that one. So it's going to be written with C kind of as part of your variable, I guess. So let's take let's look at this. Okay, so a composite function that expresses the distance driven in terms of the cost of gasoline. How far could Jordan drive her car in or on $40? Okay. All right, so the car uses gasoline at the rate of 6 liters per 100 kilometers. And that's going to be 123 per liter. So let's see, 6 liters per 100, 1,000 kilometers. And we want dollars per liter, I guess, right? So the cost of gasoline is going to be $123. That's going to be, so $123 per liter, right? Now, if I multiplied those two together, what would I get? The liters would go, I'd get dollars per kilometer. Does that look good? Dollars per kilometer. So what's 6 times 1.23, I guess? 6 times 1.23, or 6 times 123 divided by 100, so 7.38. So I've got 7.38. That's going to be dollars per kilometer, right? Or 7.38 times km, right? So 7.38 km. Let's say times k. So this is going to be the cost. Is $7.38 per kilometer. Does that look right?
But wouldn't it be 0.0738 because you're also dividing by 100?
Because it was.
No, because
Like it's a dollar.
yeah. Sorry, this was a decimal here. Thank you. Yeah, it didn't divide by 100. So that's going to be 0.0738. That's going to be in dollars. Yeah, right. Yeah, that was cents. I guess I was writing it in, but yeah, let's do dollars. It's got to be dollars. 0.07. You're right. You can see that decimal there. Okay. So that's going to be the cost. Now we have to put this into some other function, which so the composite function, the distance driven, in terms of the cost of gasoline. So so distance. So how do I use distance in terms of cost? So distance equals something, and I'm going to have to put C over here. So this is dollars per kilometer, right? So how do I get distance from cost? So cost is kind of money, dollars per kilometer, and I want kilometers, so I guess kilometers is going to have to be dollars divided by cost. So distance is money, your total, divided by the cost. So here's 40 divided by your cost function, which is $0.0738 per kilometer. Actually, so because this is, your cost is this much per kilometer, so you have to have your K down there. Yeah. So to find out how far she would go, yeah, just 40 divided by this gives you, and your units here would be kilometers, I guess. So, yeah. Anyways, you guys can do that. 40 divided by this number. I'll let you guys do that, and that would be kilometers. Because this is technically per kilometer, and then so that means that the kilometers would be up top if you're dividing by per kilometer. So that's where it goes. Okay, so you can